Hey everyone, Tim from GMAT Ninja here. Welcome to the next video in our GMAT and Executive Assessment Quant series. Today we're going to be talking about counting and sequences. And if your first instinct is to say, well, counting, that sounds a little bit basic. What exactly are we talking about here? I can certainly sympathize. That's why I threw up the question in black text on the board. Basically, when we use the term counting, we're referring to this sort of scenario where we have a defined set of numbers, usually a symmetrical set, and we're asked to find the sum of all those numbers within the set. And so we want to make sure you've got a nice, clean set of tools for dealing with these types of questions. We'll talk a little bit about how to identify the number of numbers within the set, how to leverage some of the attributes that we may be able to find along the way, like the mean or median within a symmetrical set, and also ultimately how to efficiently calculate the sum of the numbers. And then on the sequences side of things, you can see I've thrown up a sample question in red text. A lot of times we'll see it take the form of the subscript notation that we have here in terms of how the rules of the sequence are laid out for us. Not always though. Sometimes we'll have it in word problem form. So we want you to be comfortable navigating both of those worlds. If we do see the subscript notation, we want to make sure that you're comfortable with how to translate what's going on within the rules of the game. All right, so within both counting and sequences, the thing that you're probably going to hear me hammer most, and you're probably actually going to get tired of hearing from me by the end of the day, is pattern recognition. We want to make sure that we're building the muscles to identify patterns and then know what to do with those patterns that we've identified. So that'll be a real point of heavy emphasis today. As far as the questions we've got lined up for you, we've got 7 of them. 6 will be on the problem-solving side of things. 1 will be in the data sufficiency world. Nothing's going to be too crazy difficult, especially if you're able to see the patterns. That said, especially questions 1 and 4, if you're already familiar with some of this material, you've already encountered some of the counting and sequences questions. Questions 1 and 4 may be a little bit more basic for you, but stick around. We'll try and get a little bit more in the way of challenge as we continue forward in each of those individual topics, especially the last couple of questions on the sequences side of things. Hopefully those will ramp things up a little bit and give you a little bit of food for thought. That said, I'm going to go ahead and drop the first question on the screen, give you about 2 minutes to think about it, and then we'll come back and chat.
Hey everybody, Charles here. Sorry for the interruption. Before we get you back to that quant content, 3 quick things I'd love for you to be aware of. First of all, this video is part of our full, free, complete GMAT course that's available up on our YouTube channel. If this course is saving you money that you would otherwise spend on a course or a tutor, please consider donating some of that savings to charity, either a charity that you love. If you don't have a charity that you love, we've got a list of charities that we love to support on our website, gmatninja.com. Second thing, if you love that presenter that you're watching in this video, not me, the other one, they offer one-on-one tutoring. If you're interested in that, gmatninja.com and we can set you up. Third thing, finally, If you're doing great on the GMAT, doing great on the GRE, starting to look for admissions help with your applications for grad school, we would love to refer you to a bunch of our favorite companies. So just hit us up. There is a contact form on our website, gmatninja.com. Also, a link in the video description. Just fill that out. We'll send you a list of our favorite admissions consultants, not just at our company, no strings attached, not going to sell your email, not going to try to sell you anything. We just want to make sure if you've put in the hard work on the GMAT, that you end up in the best possible hands if you need help with your applications. All right, that's it. Enjoy the quant.
All right, welcome back. Feel free to hit that pause button if you need a little bit more time. Come back and join us whenever you're ready. For this question, let's go ahead and represent the length of the road that the farmer has to work with right here. Let's represent our starting point as 0, end point as 460, and we want to know how many trees we can squeeze into this space if they're 15 feet apart. And so the instinct for a lot of students might have been to just start plugging in. Okay, I'm going to start at that very beginning point with my first tree. Then the next one's going to go at 15 feet, then 30 feet, and then 45, all the way down the line until I get to something that's as close as I can get to that 460-foot mark. Well, if they're 15 feet apart, what's the nearest multiple of 15 that I can get to without going over 460? Well, okay, 20 times 15 is 300, 30 times 15 is 450, and if I try and add 15 on that, it doesn't work, so 450 is going to be the furthest tree down the line. Okay, and then as far as how many trees I've got there, well, might seem like a fairly straightforward calculation. 450 divided by the sets are... I've got spacing of 15, so I want to know how many sets I've got of 15. And really, just to clarify here, we've got that beginning point of 0, so I'm going to subtract the beginning point. If we had a different beginning point, we would want to be thinking about what the actual spacing is between the end point and the beginning point. So here, 450 divided by 15 is 30, answer choice C, and good to go, ready to move on to the next question. If that was your instinct, let's just take a quick pause here to look at some numbers that are a little bit smaller to put something in perspective here. Let's say we've got even integers, numbers 4, 6, 8, and 10. Okay, and if we wanted to know how many integers are there, I mean, obviously we can just count. Well, there are 4 integers there, but let's imagine this, right? Going through the same process that we did up here. Well, first of all, what's the distance from the lowest to the highest? In other words, subtract the lowest from the highest, 10 minus 4, and then divide by the spacing to figure out how many sets I've got. Well, here, the spacing is 2, right? I'm dealing with even integers. All of them are 2 apart. So with the same calculation, I would get to 6 divided by 2 is 3. But again, obviously, we've got 4 numbers. So why does that not work out? And what do we need to do to adjust our thinking a little bit? Well, let's take a look at one more example. Let's say we've got 12 and 14. If we tried to do the same thing, 14 minus 4 would give us a range or distance of 10 from the beginning point to the end point. And again, divide by 2. 10 divided by 2, well, that's 5. How many numbers do we have? Well, 1, 2, 3, 4, 5, 6. So we're seeing this pattern emerge where actually to get the correct number, we actually need to add 1 on. And for some of you, this may be pretty familiar. It may have been a fairly easy question, but I want to do a little bit of looking at why is that the case? What's the reasoning behind why we have to add 1 back on? So in a sense, we're kind of attaching a space of 2 to each of these numbers. So 4 comes with a space of 2, and then we've got 6, and then a space of 2, and 8, and a space of 2, kind of all the way down the line until we get to the end point. And whatever that end point is, whether it's 10 or 14 or 150, wherever it falls, we've got that endpoint that doesn't come with that subsequent spacing that all of the other numbers do. And so in a sense, we've kind of got that orphan there, and we have to, in order to represent the number of numbers, we have to go through this calculation of figuring out the distance, dividing by the spacing, but then adding that 1 number back on, in a sense, to represent that endpoint. And so let's do the same thing here. Again, this is regardless of how big the set is. If I have an equally spaced set of numbers, I have to do this same thing where in addition to this calculation, I add 1 back onto it, and that ends up getting me, in this case, 31, answer choice D. And same thing here for the spacing. It's like we've got 0 and then a spacing of 15, 15 and then a spacing of 15, all the way down to the 450, but then we don't have that additional spacing attached to it. A couple of additional points to quickly check in on. If you were distracted by that planting one tree every 15 feet, do I need to wait 15 feet into this road before I plant the first tree? The intention of this question isn't to really get you confused with that language, so I don't want you to get too sidetracked with it. But there's nothing in the language, if I read it literally, that says I have to wait 15 feet before I plant the first tree. I just know that they have to be 15 feet apart in terms of each tree that I have. And then also, if you had a little bit of a struggle towards the end in figuring out, well, like what's the closest multiple of 15 to 460, if it didn't come too naturally to get to that 450 mark, well, you could have also taken 460 and just divided by 15. You would have ended up coming up with 30, remainder 10. But that remainder 10 would tell us 460 is 10 higher than the last multiple of 15, which is 450 again. Okay, I hope that conversation was useful. We're going to continue building on this with the next question, especially the idea of why we do this and how we implement it in different scenarios. I'll go ahead and throw that next question up on the screen. We'll talk about it in about 2 minutes. All right, welcome back. Feel free to hit that pause button if you need it, as always. Here we've got Regina at the beginning of her savings journey. She's got $100 in her account, and she's going to start adding to that, making a deposit every week, starting with $30 and then increasing the deposit amount by $3 every week. We want to know, by the time she makes that $90 deposit, what's she got in her account as the balance? So a way we could represent that question is just that $100 that she starts with plus all of her deposits, the sum of all those deposits that she makes over the period that we're concerned about, equals what? And so the main thing that really is tricky as far as calculation is just how do we have an easy way of summing up the deposits? And we could represent sort of what we're dealing with here just by writing out the amounts of the deposits to start with. We've got 30, 33, 36, 39, etc. And then we get all the way down to the final two deposits of $87 and $90. And so, boy, we don't really want to go through the laborious process of adding all of these numbers up. So do we have a workaround to more quickly get to that total? Well, you may or may not have some type of a formula rolling around in your mind for how to sum the number of numbers in a sequence, or how to sum all the numbers in a sequence. If you don't, my guess is that you at least have this in your mind, either explicitly or implicitly. You know what an average is, right? Average is just the total of all the numbers in a set and then dividing it by the number of numbers we've got. So the reason we bring that up is because you notice that does have the word sum in it, and we can rearrange that to calculate for the sum. And so if we know the average of the numbers as well as the number of numbers in a set, then we can find the sum. So how do we do that? How do we find the average of all of Regina's deposits? Do we know the number of deposits that she makes? Well, let's see here. Let's try and apply this formula. And let's hold off for a moment on the average. Let's look at the number of deposits first, because you may recognize some similarity between what we have going on here and what we talked about in the last question, where we've got a beginning point as well as an end point. First deposit is 30, last deposit is 90, and we just recognize those additional deposits. Everything in between has even spacing. They're all $3 apart. And so our beginning point and end point, we can represent. That range is going to be 90 minus 30. Then to figure out how many sets, or in this case, how many deposits we have, we're going to divide by 3 and then again add the 1 back on. Just like we said last time, we've got 30 and then a spacing of 3, 33, and then a spacing of 3. We've got this 90 endpoint at the end, and if we just do the 90 minus 30 divided by 3, that doesn't account for that extra 90 that doesn't have that spacing of 3 with it, so we have to add the 1 back on. Cool. How about the average? So for a moment, I'm going to have us just look at a subset to illustrate something. So we've got the numbers 30, 33, and 36. What would be the average of that set of numbers? You may very well, without actually doing any calculation, be able to say, oh, well, that's 33. Okay. Well, if we did the calculation, we'd end up with, yes, 99 divided by 3 equals 33. Cool. And then if I asked you, how about the median? Well, the median's the middle number in a set when they're ordered from lowest to highest. And in this case, 30, 33, and 36, well, it's the same as the average, right? 33. Well, what happens if we extend that out by 1? Let's just look at these 4 numbers. Add 39 into the mix. Now our sum is going to be 138. You don't have to worry about doing the calculation right now. 138 divided by 4 is 34.5. Well, if we tried to do the same thing with finding the median, we would say, well, it's the middle number, but if we don't have a single middle number, if we've got an even number of numbers in our set, then we have to average those two middle numbers, 33 and 36. The average of those is going to be 34.5 as well. So why do I bring that up? Well, the punchline to take from that is that the average and the median are always going to be the same if we have a symmetrical, equally spaced set of numbers, which is what we have here, right? Everything is 3 apart. And so the average is going to equal the median, same thing. How do we find the median? Well, to find the middle number, if it's an equally spaced set of numbers, all we have to do is take the average of the highest and lowest numbers. So in this case, that's going to be 30 plus 90. And then to find the average of those two, we just divide by 2. That's going to give us the average. One quick detour that I want to take here is that we recognize 30 and 90. Those, in this case, are both dollar amounts of actual deposits that we have. Those are numbers that fit our set. Sometimes you may have a question that asks you for example, the sum of all odd numbers from 100 to 200. And in that case, it could get a little bit tricky because 100 and 200, those are not odd numbers. So in that case, we actually want to take the first and last numbers that fit our criteria. So in that case, it would be 101 and 199. Those would be our endpoints, our first and last numbers. And so especially with respect to the number of numbers, it's important for us to be thinking that through pretty carefully. That said, in this case, we don't have to worry about that. We can just do the calculation here. 30 plus 90 over 2, 120 over 2 is going to be 60 times, and then 30, we've got 90 minus 30 is 60, divided by 3 is 20, plus 1 gives us 21. And here we could take that all at one bite, go ahead and do the multiplication, or we could take that as 60 times 20 plus 1 and do the multiplication separately. 60 times 20 is 1,200, plus the extra 60 that we have from the 60 plus 1 would give us 1,260. Answer choice B seems to line up with that. And if that's what you went for, then I'd point us back to step 4. Step 4 of the process, again, is read the question one more time. We're actually asked how much she's going to have in her account, not what the total of her deposits is going to be. Again, when we wrote the question down, we said 100 plus the sum of all her deposits. So in this case, that's going to be answer choice D, 1360. This is a pretty classic counting type of question. So I want to make sure that we have on lockdown this process in terms of identifying the average when we've got a symmetrical, equally spaced set of numbers, which is going to be the typical scenario that the GMAT's going to throw at us for a counting question. This is how we find the average. Take the highest and lowest numbers that fit the criteria within the set. Just find the average of those numbers. And then the number of numbers, same type of scenario that we looked at last time. All right. I hope that was helpful. We're going to keep building forward on top of this. I'll throw the next question on the screen, and then we'll talk about it in roughly 2 minutes. All right, go ahead, hit that pause button if you need to, as always. So what have we got going on here? Housing developer that keeps gobbling up properties until all 9 of the properties in this small town have been purchased for a total of $49,500. We know each property sells for $1,000 more than the prior property. And the question is, what is the price of this 7th property? That's the one that we want to figure out. So a lot of students might have an inclination to say, well, I know that all 9 of these properties are going to have a total of $49,500. So I'm just going to algebraically express everything that we've got. I'm going to start with the first property. I'm going to represent that as x. Second property is just going to be x plus 1,000. I know that all of them are 1,000 more than the prior. So third one is going to be x plus 2,000. And you can imagine we could continue filling this out until we get to the ninth property. That's going to be x plus 8,000. So going to fill in all of these and then add all of those numbers up, solve for x with that equation, and that should give me the value of the first property. I recognize the seventh property is going to be x plus 6,000. And then once I have solved, I should be good to go. Mathematically, algebraically, that's just fine. At the same time, a couple of things that I don't love about that. Number one, it's probably going to take a bit more time than we want on a typical GMAT question to work through all of that addition and then solving. Secondly, by the time I do all that addition, there are enough opportunities where I might potentially go off the rails in terms of calculation errors that I'd rather that not be my path if I can avoid it. Some students may see an opportunity for a little bit more efficiency and say, well, I'm going to represent x as representing the value of the seventh property. And again, all this is going to total to 49,500. So same end destination there. But because I'm representing the seventh property as x, the eighth property is going to be x plus 1,000. The ninth property is going to be x plus 2,000. And then going downwards, I'm just subtracting x minus 1,000 for the sixth property, x minus 2,000 for the fifth property, and on down the line, x minus 3, 4, 5, 6,000. And then I'm going to add those up, solve for x, and x in that case is going to be the value of my seventh property. Probably a little bit more efficient than the first path, but I also want us to take a look at what I think is an even better path forward. So a lot of counting in sequences is testing your ability to spot patterns. Did you recognize on this one that we have a symmetrical, evenly spaced set? And if you did that ring a bell from our past couple of questions? I certainly hope so. So what can we do in a symmetrical, evenly spaced set? Well, we recognize that equation of sum equals average times the number of numbers still applies. Well, why would that be useful here? We're looking for the value of the seventh property, or the sales price of the seventh property. So we do know the sum. Yeah, okay. So we know that's 49,500. And then we don't know the average, right? So that's something that we'll just have to represent here. And do we know the number of properties? Well, sure, we've got that, 9. So we could go ahead and solve for the average. What would be the purpose behind that? I don't want to just mindlessly start doing calculations, but if you reach back to that last question that we discussed, you may remember in a symmetrical, evenly spaced set of numbers, the mean or average equals the median. Ooh, now suddenly that sounds really interesting. If I know I'm going to be able to calculate the value of the fifth property out of the 9, that would be the median, the middle one, right? By finding the average, hey, that's great. So I'm going to go ahead and move forward with that, recognizing what I'm going to do with it. So if I rearrange that equation, 49,500 divided by 9 is going to be the average. May have to do a little bit of calculation over here on the side of the board. Okay, 49.5 divided by 9, that's not too bad. 49 divided by 9, okay, that gives me 5. Carry the 4, I've got another 5 here. 5,500 is going to be my average, which again also equals the median. Put that in the fifth slot, and suddenly it's really easy for me to fill in any of these spots. I just know I'm going downward by 1,000 with each one here, upward by 1,000 here. We're looking again for the seventh, the sales price of the seventh one. That's just going to be 2,000 more than the median of 5,500. 7,500, answer choice C is what we're looking for. So again, counting and sequences both, testing your ability to recognize those patterns and what we can do with them. Here, if I see that, recognizing, hey, this is one of those scenarios where I can use this equation, and I also can use the mean to find the median, and I'm off and rolling from there. If I see that, then I'm in great shape and should have a fairly efficient solution. All right, we're going to move out of the counting hemisphere and into the sequences hemisphere with this next question. I'll throw it up on the screen, then we'll talk about it in roughly 2 minutes. All right, welcome back. Feel free to hit that pause button if you need a little bit more time. On the other hand, if you'd say, man, this question felt pretty straightforward. I'm pretty comfortable with sequences, the basics at least, and subscript notation. I understand how that works. This may be your cue to go ahead and fast forward to the end of this discussion. Just double check, make sure you got the question right and that nothing tripped you up. But on the other hand, if you are a student who would say this type of scenario feels kind of like gibberish to me, I'm not sure exactly what's going on, some moving parts here that are unfamiliar, no problem. That's what we want to unpack. So in this type of scenario, we've got an equation that basically gives us the rule for how this type of sequence functions. And so this is pretty classic type of scenario in terms of what the GMAT often gives us. Some type of equation that gives us the rule, and then they give us a value for one of the terms, and they ask us to find some other term. And in this case, we know that a sub n equals a sub n minus 1 plus 5. What does that actually mean? Well, as far as the component parts, the a is just something I would think of as the label for the sequence. We'll call it sequence A. I'm not as concerned about that as I am about the terms, the subscripts there, and also what happens here with this plus 5. So the way I interpret this is for any term in the sequence, we'll call it the nth term or term number n, that equals the previous term. So the n minus 1 term, the one that comes before term n, plus 5. So to make that a little bit more concrete with numbers instead of variables, the 13th term in sequence A equals the 12th term in sequence A plus 5. Or to kind of carry that to the next step, the 14th term equals the 13th term plus 5, and then you could kind of see the progression just kind of continuing the same pattern all the way down. And then the information we're given is a value of a sub 6, that's 100, and we're asked to figure out what a sub 66 equals. Okay, cool. And one of the things that we also want to be bearing in mind here is that, we get to a sub 17 at the end. What happens basically with each forward movement along the way from A13 to A17 is that we're just doing the same thing with each forward step from one term to the next. Each forward step is adding on 5. And so that's one of the questions that I want us to be really clear about when we encounter this type of a sequences question. Just what happens with each step. And most often, we're going to be presented with what happens with a forward step in terms of the equation we're given. But sometimes we'll have to think about what happens if we take a backward step just in terms of what we're ultimately being asked. We may have to kind of think of it in the other side of the equation. But what happens with each step, and then how many steps are being taken? So here we would say, well, what happens with each step is we're adding 5. And that happens between A13 and A17. That happens 4 times. And so another way of thinking about A sub 17 is not only as A sub 16 plus 5, but also as A sub 13 plus what? Well, we end up adding on 5 4 times, so we add on 20 total. But I think here it's helpful to represent that as 4 times 5, where we recognize, hey, we're figuring how many steps we take, and then taking that times the increment that we increase by each time. So now as we move to A sub 66, and we want to know the value of that, how do we represent it? Well, kind of following this pattern right here, we could just say, well, A sub 66 is going to equal A sub 6 plus, then what are we going to add to A sub 6? Well, we've got a distance between 6 and 66 of, instead of 4 like we had here, well, 66 minus 6 is 60. And that's what we're going to take times 5. So then replacing the A sub 6 with the value that we actually have for it, we could say that's going to be 100 plus the 60 times 5 is 300, which equals, at the end of the day, 400. So answer choice C, 400. And again, this is really foundational to our understanding of what to do on a sequences question. Want to make sure that this is on lockdown in terms of understanding what to do here. The questions I want to ask in this type of scenario are these 2 in green. What happens with each step that I take, and particularly that's typically going to be framed initially in terms of a forward step. And then how many steps are being taken. And if those are forward steps, then great. If I need to think of them as backward steps, then I can kind of adjust the math from there. But that's the essence of what we need. The additional questions that we're going to look at are largely playing with some of these concepts and building on this foundation. We'll get you into a word question next. And so I'll give you a couple of minutes, put that on the screen, and then we'll come back and talk about it. All right, here's your chance to hit that pause button if you need it. If you're ready to roll, so am I. What have we got going on here? Well, population of guinea pigs, doing what guinea pigs do. We start with population of 10, and those are just going to double every month. And we want to know over the next 6 months, how many do we add to the population? So we've talked a little bit about how counting and sequences questions are largely about recognition of patterns. Did you spot the pattern here? And first of all, did you recognize it as a sequences question? It may be presented in word form, but it is most definitely a sequences question. And in fact, we do have a rule. We have to do a little bit of translation. It's not as explicit as it was in the prior question, but we've got it. So what are we going to translate as the rule? Well, a sub n equals a sub n minus 1 with what done to it? The last question, we were adding 5. In this case, when we move from the prior term, in this case, that's the number of guinea pigs that we have in a given month. What happens when we move to the next month? Well, we just double that prior population, right? So going to take that times 2. All right, with that in view, we also know a sub 1 is going to be 10. If we represent a sub 1 as the number of guinea pigs that we have at the very beginning, at our starting point. So with that in view, what do we know? Well, first of all, we know what happens with each step here, right? Every time we move a step, we're going to be doubling, right? Doubling the population if a step represents movement from one month to the next. So a sub 2, so population at the beginning of the next month is going to be 10 times 2. And then a sub 3 is going to be that number from the prior term times 2 again, 10 times 2 times 2. Same deal if we get to a sub 4, it's going to be 10 times 2 times 2 times 2. And at this point, you may be able to see a pattern emerging. And yeah, as we're doubling, we're just adding 2 as a factor each time. And by virtue of doing that, we are actually playing in the world of exponents now. And that's what happens when we have this type of a rule where instead of adding or subtracting, like last time we were adding 5, if instead we are multiplying, now we've got exponents going on. How would we represent that? Well, a sub 2 equals 10 times 2. We could also call that 10 times 2 to the first power. A sub 3 equals 10 times 2 to the second power. A sub 4 equals 10 times 2 cubed. And so you can see the progression here of exponents, and that number that we have as an exponent is going to be equivalent to the number of forward steps we've taken, because that's how many times we're multiplying by 2. Move from step A or from term A1 to A2, we're multiplying it by 2 once. From A1 to A sub 3, multiplying it by 2 twice because we've moved 2 steps. A sub 1 to A sub 4, 3 steps. Okay, so you get the idea. And we could continue moving on down until we have taken the appropriate number of steps. We're wanting to know what's happened by the time we're 6 months out. So 6 is going to be the number of steps that we're shooting for. We could recognize, hey, that term is going to be what we'll call A sub 7, going from A sub 1 to A sub 7. That's the movement of 6 forward steps. And so that also is going to be equal to 10 times 2 to the 6th power. So that's what we're looking for as far as the place that we want to get to in time. And we could recognize 2 to the 6th is 64. So that ends up multiplying out to 640. And we've got a lovely answer choice E that I hope you did not go for. If you did, what did we miss? Step 4 of the quant process. Read that question one more time. How many additional guinea pigs will be added to the population in the next 6 months? So this represents the number of total guinea pigs we have at the 6-month mark. We recognize we started with 10, so we have to subtract that 10 back off to figure out how many additional guinea pigs we've got. Answer choice D, 630 it is. All right, like I said, from here, a lot of it's going to be about pattern spotting. The last 2 questions will begin to ramp up the difficulty level. So I'll throw the next one on the screen, and we'll look forward to chatting about it in roughly 2 minutes. All right, welcome back. Give you a chance to hit that pause button if you need to. This question gives us our first dip into the waters of data sufficiency. So I have put the trusty AD-BCE tool up for the using. And this question may have felt a little bit different from the prior sequences questions, and that's because it is different. But it might take a moment to kind of wrap the brain around, well, why is it different? What's different about it? And I would point us to the way that the rule is structured here. Because in the prior cases, we had a scenario where we were expressing the rule for what one term equals in terms of what we do with one prior term. So in those cases, it was a sub n minus 1, and we do something with it. We either add 5 or multiply by 2, or we could have had a situation where we subtracted or divided. But in any case, that scenario is one in which we're doing the same thing with each forward step from one term to the next. And so that allows us to use the approach that we talked about, where it's like, okay, I want to figure out what each step consists of, and then how many steps I'm taking, and then kind of make the calculation from there. Here it's a little bit different because we're actually defining a term in terms of two prior terms, a sub n minus 2 divided by a sub n minus 1. And so that skews things a little bit. We can't just take that same approach that we took previously, because we're not going to be just adding 2 or multiplying by 5 or whatever the case may be. And so in this case, we end up kind of having to play around a little bit with the information we've got and figuring out what we can do with it and how we can sort of pin down values of various terms. I am going to go ahead and re-express this, kind of rearrange this equation, just because it's a little bit easier for my brain to process. So if we rearrange this, we recognize this is the same thing as a sub n times a sub n minus 1 equals a sub n minus 2. And for some students, that may not really feel much different than this as far as how your brain processes it. For me, it is a little bit easier if I'm not dealing with a fraction, having a numerator and denominator. So I can kind of grasp what's going on here. It's like, okay, well, if I take any term and multiply it by the immediately prior term, that is going to equal the term that was 2 prior. So 2 terms ago. Okay, like I get that. And just to make it that much more concrete, we could actually represent it with some numbers here. So let's say that we've got a sub 6 here. And just to define what it is that we're actually chasing, let's go ahead and represent our question, which is just what is the value of a sub 6? So that's why I'm putting that here to start with. A sub 6 times a sub 5 equals a sub 4. Okay, and then I could also place a sub 6 in a different spot in the equation. And in that case, I would have a sub 7 times a sub 6 equals a sub 5. I could also place a sub 6 all the way over here on the right. And in that case, it's going to be a sub 8 times a sub 7 equals a sub 6. Cool. And so you can see we could continue playing this pattern out up and down. And one thing that I notice here is if I have 2 out of any 3 consecutive terms, then I've got enough to solve an equation somewhere. So if I've got 4 and 5, I could solve for 6. If I've got 4 and 6, I could solve for 5, or 5 and 6, I could solve for 4. Cool. And that then also would unlock everything else up and down. Once I've got a sub 5 and 6, well, that gives me enough to plug in values here, and I could solve for a sub 7. And then once I've got 6 and 7, I could solve for 8. And I could go back up the other direction too, right? I could have a sub 5 times a sub 4 equals a sub 3. So I could just keep working up and down as long as I have somewhere 2 out of any 3 consecutive terms. If I have those values, should be good to go. So that is a big piece to unlock here before we go ahead and look at the statements. With that said, let's go ahead and check out statement 1. We know the product of the 7th and 8th terms is 1 over 3,125. Well, that actually tells us directly the value of a sub 6, right? We know that this times this equals 1 over 3,125. We've already unlocked the value of a sub 6, so we don't actually have to do anything else there. Second statement, the third term is 5, so we've got a sub 3 in this case is 5, and the fifth term is 125, so we've got that. which would then, again, allow us to solve for a sub 4. Once we've got a sub 4 and 5, then that would allow us to solve for a sub 6 as well. So statement 2 is also sufficient. I should have crossed this out at the beginning when we evaluated statement 1, narrowed down to A and D. After we say statement 2 is sufficient, we're left with answer choice D. And boy, again, this one just really hinges on a lot of ability to see patterns. So hopefully those muscles develop as you see more of these question types. I'm going to throw one more at you that'll maybe ratchet up the difficulty level just a little bit more. Again, it kind of depends on whether you're able to spot the pattern or not. I'll throw it out there on the screen, give you a couple minutes, then we'll come back and chat.
All right, 2 last things. Thank you so much for making it to the end of the video. If you've made it this far, you're one of those awesome people that's obviously really engaged in this GMAT thing. We would love your comments and your feedback. If there's anything else you'd love to see in our videos, hit us up in the comments. We'll do our best to oblige. Second thing, if you're enjoying it, hit that like button, hit the subscribe button. Helps other test takers like you find our full free video course. You need anything else? You know where to find us, gmatninja.com. Thanks so much. Enjoy this last question.
All right, we are on the home stretch now, my friends. If you need to take that one final opportunity to pause, go ahead and do so. If not, let's dive on in. And this question is one that I would imagine could be a little bit polarizing. Probably we've got students in one camp who would say, man, this was kind of a beast. And probably students in another group who would say, actually, it felt kind of like a breeze. And probably the difference for most students is going to come down to that thing that we've emphasized multiple times throughout this video. Were we able to spot the patterns? And this question kind of illustrates what happens in many sequences cases where the GMAT is kind of ratcheting up the difficulty level in appearance, at least, in the sense that as we first look at this, it feels like, man, we've kind of got a lot of ugly numbers, could be a little bit intimidating at the outset. But then if we actually start to work with what we've been given, there comes a point at which things kind of unfold and we realize, oh, actually, things just simplify down pretty easily here. And a lot of times that moment is going to take the form of a lot of numbers canceling out at once. That's what ends up happening here. If we don't see that, then we're going to be here for a while probably. That said, one of the things that we want to think about is the step 2 of the quant process, the path plotting step, because we want to be intentional about what we're doing and we don't want to just mindlessly start performing calculations. With some of these sequences questions, there is a sense in which we sort of need to peel back the layers of what we've got a little bit more, maybe one step at a time, without being 100% sure of what the final outcome is going to be. but we've still got an intentional path forward. The path is to say, hey, I'm going to try and represent what I've got. Okay, now that I've represented what I've got, I'm going to try and express it in a little bit more simplified way. And then if we still can't figure out a path forward, then okay, we again don't want to just get lost in the wilderness and stuck for like 4 minutes or something like that. But it's okay to do a little bit of exploratory work because we know that that tends to be the nature of some of these types of questions in particular. So let's go ahead and get into it. So we've got a sub n equals 1 plus 1 over n. And the question here is if p is basically the product of all of those numbers, all of those terms from the second term to the 100th term, where n is an integer, then what's the value of p? So I'm going to go ahead and represent that here. P equals what? And let's go ahead and plug in some numbers to represent a sub 2 and a sub 3 and a sub 4 so we kind of have a little bit of a grasp of what it is that we're doing. Let's make this concrete here. So a sub 2 would be what? 1 plus 1 over 2. Okay? A sub 3 then would be 1 plus 1 over 3. A sub 4, 1 plus 1 over 4. And we could keep going on down the line until we get to our last terms. Let's go ahead and put the last two. A sub 99 is going to be 1 plus 1 over 99. And a sub 100 is going to be 1 plus 1 over 100. So that whole thing, we want to know what that equals. And it's important for us to do this step because sometimes this is the place where we're going to see that cancellation or sort of the pattern emerging. And here we don't necessarily hit that just yet, but we recognize, hey, there's another form, another way in which we can express these mixed numbers, 1 plus 1/2 or 1.5. That's the same as 3 over 2. And I'm going to go ahead and do those improper fraction forms here and see what happens. 3 over 2. Well, 1 plus 1/3 is going to be 4/3. And 1 plus 1/4 is going to be 5 over 4. Kind of keep going on down the line. And then at the end, we end up with 1 plus 1/99. Well, that's going to be 100 over 99. And then 1 plus 1 over 100 is going to be 101 over 100. And we want to know what that equals. Hopefully at this point you can see, and maybe it would help if we kind of stretch this out to one more and said, oh, well, the next one is going to be 6 over 5. But I think we can kind of see the pattern developing, right? We're going to have, at each stage, we're going to have a numerator that matches the next denominator. And so things are just going to kind of keep canceling out down the line. We would have a 6 over 5, so we'd have a cancellation of the 5 here. And then that's going to keep going until we get down to the 100 over 99. Well, we're going to have a 99 denominator that matches the previous numerator in a 99 over 98. And then the 100 matches this. And so at the end of the day, everything cancels out except for the very first denominator and the very ending numerator. So we're left with 101 over 2, which we also know equals 50.5. Answer choice C is in fact what we're looking for. So again, there was this moment where kind of the curtain was pulled back and we saw where all of the cancellation would happen. It ended up being pretty easy by the time we got to that. Yeah, this tends to be the punchline for a lot of the more challenging sequences questions. Are we able to spot a pattern? Sometimes it takes a little bit of work to get to the point where the pattern emerges. And so we need to be patient without, at the same time, just kind of mindlessly doing a bunch of calculation. We want to be purposeful in terms of the path that we take. Okay, I hope this was helpful. Just kind of recapping what we've looked at today. On the counting side of things, yes, there were some patterns, some things that we discovered, as well as some of the basic tools that we really want to have on lockdown. We want to make sure that we know what to do with that sum equals average times the number of numbers formula anytime we've got a series of evenly spaced, kind of a symmetrical set of evenly spaced integers or other numbers. And so be prepared to work with that, kind of know how to apply that formula and manipulate it inside and out. And then on the sequences side of things, make sure when we have that basic subscript notation, we know what to do. as far as identifying what a forward step looks like and how many steps we have, kind of how to make calculations from there. And then when we have other types of sequences, just try and be as flexible as possible, try and identify the patterns that we've got, and work with the numbers that we're given. All right. Well, as always, we appreciate you tuning in. We look forward to hearing from you in the comments or otherwise. If there's any way we can support your journeys towards graduate school, we're excited to do so. Thanks again for taking a look at this video. We look forward to seeing you in the next one.